We have now come to a right understanding of the idea of independence in probability. It is now time to test our understanding on examples which will stretch our capabilities a little bit. So let's begin immediately with a question of ranking. So imagine that we have four protagonists. Let's call them P, Q, R, and S. Think of them as athletes or students. Let's say the athletes run a race. We are going to rank the athletes in order from the fastest to the slowest, or if you are students, from the highest rank to the lowest rank. Imagine, of course, that in this setting, all possible arrangements of rankings are equally likely. What is a natural probability space for this model? So let's begin it one step at a time. We naturally want a sample space. The sample space here is the allocation of order to the four athletes P, Q, R, and S. In other words, we've got a four-tuple of individuals, and every possible permutation of those four tuples is a valid sample point. How many possible permutations are there? Well, there are 4 factorial permutations, or 24 possible permutations. Therefore, the sample space is all 24 permutations of the letters P, Q, R, and S. Let's put in place some events of interest for us. So let's start with an event A, which connotes the possibility that athlete P ranked ahead of athlete Q. P was ahead of Q. Of course, this is in ordinary language. But it is an event, and therefore it is a subset of the sample space we have identified. Which subset is it? Well, I won't write down all the possibilities for you, but now it should be easy enough to imagine. I want to look at all strings of 4 letters where P appears before Q. Here is another event, call it B, that R leads S. Likewise, all 4 tuples where R appears before S. In principle, we could enumerate it, but it is sufficient now to understand what the structure of this event is. The probability measure, naturally, is combinatorial. All possibilities are assumed to be equally likely, so we are dealing with an atomic measure which puts equal mass 1 over 24 on each atom, on each permutation. Let's compute probabilities. Right? Our basic question is, are A and B independent? Now, to do this, we have to understand the probability of A, we have to understand the probability of B, and we have to understand the probability of A intersection B. And then we query, is a rule of products satisfied? This is the acid test for independence. Let's go step by step. What can we say about the probability of A? Now, if P is to be ahead of Q, we can decompose it in the following ways. P could be the first. If that's the case, then P will certainly be ahead of Q, and Q will have 3 possibilities. Or P could be second, but in that case, for P to lead Q, Q must be in one of the 2 possibilities following P. Or P could be in the 3rd place, and if that's the case, Q must be in the last place if she is to follow P. And therefore, there are 3 plus 2 plus 1 possibilities for putting Q to the right of P. Having put P and Q in place, there are 2 slots left, and R and S will have to occupy those 2 slots. How can you arrange R and S in there? Well, in 2 factorial or 2 ways. And therefore, there's a total of 3 plus 2 plus 1 ways of arranging P and Q, with Q following P, 2 ways of arranging R and S in any order you like, and totally you get 6 times 2, or 12 possibilities for P leading Q. 12 outcomes which are favorable for the event A, that P leads Q. How many possibilities in total? Well, the total number of outcomes is 24, or 4 factorial, and therefore the probability that P leads Q, the probability of the event A, is 1 in 2. Of course, barring a change in names, an exactly similar calculation holds for the probability that R leads S, for the probability of the event B. Therefore, both the probabilities of the events A and B have a chance 1 and 2. What can I say about the intersection? Well, the intersection of A and B means P leads Q and R leads S. Well, let's start by putting Q to the right of P. How many ways are there of doing that? As we noticed, 3 plus 2 plus 1 ways. Now P and Q are allocated with Q following P. There are 2 slots left, but if R is to lead S, they are compelled now with R taking the leading slot and S taking the last slot. Therefore, once you placed P and Q, R and S are also placed, and therefore there are 3 plus 2 plus 1 outcomes favorable to the joint occurrences of the events A and B. Again, out of 24 possible outcomes, and therefore the chance of A intersection B is 1 in 4. Now, to test independence, we find that 1 in 4 is just 1 and 2 times 1 and 2. And therefore, the probability of A intersection B is given by a product of the probabilities of A and B. And we conclude by fiat of definition that the events A and B are independent. Did that surprise you? On introspection, looking back at the problem, perhaps you can convince yourself, of course they are independent, because the relative placement of P and Q doesn't depend upon the relative placement of R and S in terms of the chances. That seems very reasonable, very intuitive, and it is correct.